Good morning to one and all. I present this lecture mainly for 3rd BSc Chemistry students of our college during the critical situation of COVID-19 pandemic. This topic, photochemistry, is present in Physical Chemistry 1 syllabus of our Bharadasan University. Physical Chemistry 1 consists of 5 units. First unit consists of 2 chapters. One is photochemistry, another one is group theory. This lecture is on the topic photochemistry. First, I want to read the syllabus regarding photochemistry. Unit 1, Photochemistry and Group Theory. 1.1, Consequences of Light Absorption, Jablonski diagram, Radiative and non-radiative transitions, Lambert's-Beer law, Quantum efficiency. 1.2, Photochemical reactions, comparison between thermal and photochemical reactions, photosensitization and quenching, fluorescence, phosphorescence and chemiluminescence, laser and uses of lasers. Photochemistry. Photochemistry is the branch of chemistry which discusses the effects caused by light. Next, photochemical reaction. Now, what is photochemical reaction? Photochemical reaction is a reaction caused by light. For example, photosynthesis. In the case of photosynthesis, carbon dioxide, it combines with water in the presence of sunlight and in the presence of photosensitizer chlorophyll. We get the product, carbohydrates is the main product and oxygen as the byproduct. This slide shows clearly the photosynthesis process. Here 6 moles of water combines with 6 moles of carbon dioxide gives 1 mole of glucose and 6 moles of oxygen. Next, laws governing absorption of light. Next one is Beer's law or Lambert-Beer's law. It is very simple law. This is the only law which is included in the syllabus. It states that when a monochromatic light is allowed to pass through a homogeneous absorbing solution, the rate of decrease in the intensity of monochromatic light with the thickness of the solution is directly proportional to the intensity of incident light I and also to the concentration C of the solution. That is minus di by dx is directly proportional to IC. Now that is equal to K dash IC. Now on simplification and on integration we get another equation. That equation is I is equal to I0 e power minus K dash Cx. That can be written as IT, otherwise written as IT is equal to I0 e power minus K dash Cx. Here IT, that is the intensity of transmitted light, I0 intensity of incident light, K dash molar absorption coefficient, C concentration of the solution, X is the thickness of the solution. Now that can be, this equation can be written as in 10 power equation, that is IT is equal to I0 10 power e power minus epsilon dash Cx, where epsilon dash is molar extinction coefficient, that is equal to K dash divided by 2.303. These are about Beer's law or Lambert-Beer's law, both are same. Now this law is frequently asked in the university examination. Now comparison of photochemical reaction and thermal reaction. Another name for photochemical reaction is light reaction. Similarly, another name for thermal reaction is dark reaction. So now what are the differences? One difference, in the case of photochemical reaction, these reactions involve absorption of light radiation. But in the case of thermal reactions, these reactions involve absorption or evaluation of heat energy. That is, during thermal reaction, heat may be absorbed or it may be evolved. So that is one difference. Another difference, energy of activation is gained by absorption of photons. So energy of activation means that is minimum energy of reactant molecules to form the product. So in the case of photochemical reaction, EA is gained by absorption of photons, but in the case of thermal reaction, EA is gained by collision of reactant molecules. That is another difference. And third difference, presence of light is the primary requirement for photochemical reaction, but in the case of thermal reaction, light is not the requirement. And another difference, fourth difference, in the case of photochemical reaction, molecules are strongly excited by absorbing photons. But in the case of thermal reaction, even by a significant rise of temperature increases the average energy of molecules to a small extent. That is another difference between photochemical reaction and thermal reaction. Another difference is temperature has very small effect in the case of photochemical reaction, but in the case of thermal reaction, temperature has significant effect. And another one, delta G, delta G means free energy of products minus free energy of reactants. In the case of photochemical reaction, it may be positive as sum of light energy is converted to free energy of products. So in the case of photochemical reaction, free energy of uh, product is greater than free energy of reactants. But in the case of thermal reactions, these reactions involve in the decrease of free energy. That is, delta G is always negative in the case of thermal reaction, but in the case of photochemical reaction, delta G may be positive. So in the case of photochemical reaction, delta G may be positive, but in the case of thermal reaction, delta G is always negative. Another difference is photochemical reaction, photochemical activation is highly selective process in the case of photochemical reaction. But in the case of thermal reaction, thermal activation is not selective in nature. So these are the differences between photochemical reaction and thermal reaction. Question may be asked, what are the differences between photochemical reaction and thermal reaction? Next one is photophysical processes. A molecule A is excited to A1 star by absorbing one photon. Now this process is called as activation. That is, the molecule is excited to higher energy state. Now the molecule A1 star has sufficient energy. Now this molecule is converted to product. Now that is the photochemical reaction. Suppose the molecule A1 star has the energy is, suppose the energy is not sufficient, then the higher energy molecule, A1 star molecule, activated molecule, is deactivated under various pathways. Now the various pathways of deactivation of an excited molecule is grouped under photophysical processes. Now here A is the ground state molecule, A1 star, that is excited state molecule in singlet state. Now the various pathways of deactivation of the A1 star, that various processes are called as photophysical processes. So photophysical processors, it consists of two process, two processes. That is, one process, that is the excess energy is liberated in the form of heat, that is non-radiative transition. Another one is the excess energy is liberated in the form of radiation, that is called radiative transition. So the excess energy may be liberated either in the form of heat or in the form of radiation. If the excess energy is liberated in the form of heat, then the transition is non-radiative, otherwise called as radiation-less transition. If the excess energy is liberated in the form of radiation, then that type of transition is called as radiative transition. This slide shows representation of radiative and non-radiative transition. The radiative transition is given by straight line arrow, but in the case of non-radiative transition, the transition is represented by curly arrow, that is curly arrow or broken lines arrow, as shown in the figure. Jablonski diagram is the diagram which shows all the photophysical processes. So I have already told there are two photophysical processes mainly. One is radiative transition, another one is non-radiative transition. Radiative transition means liberation of excess energy in the form of radiation. Non-radiative means excess energy is liberated in the form of heat. Here this diagram shows all these transition. Here one is IC, that is non-radiative transition. Another one is ISC, that is also non-radiative transitions. And the radiative transitions are fluorescence and phosphorescence. So all these are shown in the diagram. That diagram is called as Jablonski diagram. Here first the molecule is excited from S0 level to S2. S2 means S1, S2 means these are singlet states. Singlet states means spin multiplicity, that is equal to 1. Here two electrons in the ground state, one electron has opposite spin to that of another. So the total spin angular momentum, that is equal to half plus minus half. So total spin angular momentum is equal to 0, but the formula for spin multiplicity, that is given by 2s plus 1. 2 into 0 plus 1, that is equal to 1. That is spin multiplicity. So in the left hand side, the states, all the states, that is lower ground state and exit states, all are singlet. That is clearly shown in the diagram. But in the triplet state, the electron is excited with the inversion of spin. That is, both are having plus half value. So total spin angular momentum is equal to half plus half, that is equal to 1. And spin multiplicity formula 2s plus 1, that is equal to 2 into 1 plus 1, that is equal to 3. So the spin multiplicity is 3. So T1 is the first excited triplet state and T2 second excited triplet state. So this diagram shows various photophysical processes. So we can see what is IC, what is ISC, what is fluorescence, what is phosphorescence. All these are discussed in the coming slides. This slide shows explanation of Jablonski diagram. Here, the first step is the non-radiative transition from higher excited singlet state, that is Sn, to the lower excited singlet state, S1. That is the first excited singlet state. This is called internal conversion. Both are having same spin multiplicity, and here the transition is non-radiative. So this is called internal conversion. Simply it is IC. Now from S1 molecule, the molecule return to ground state by any one of the following paths. Path 1, the molecule may lose rest of the energy also in the form of heat, so that the complete path is non-radiative. That is Sn to S1 with the liberation of heat, that is internal conversion, or S1 to S0 with the liberation of heat, that is also internal conversion. Path 2, that is another deactivation of excited state molecule in the state S1. That is, the molecule releases energy in the form of light or UV radiation. This process is called as fluorescence. Both are in singlet state, but the transition is radiative. So this path is radiative and the process is fluorescence. Now path 3, another pathway. Some energy may be lost in transfer from S1 to T1 state in the form of heat. That is, a molecule in the S1 state liberates its excess energy in the form of heat, and it becomes in the state T1. Now this process is non-radiative, but the transition is from singlet to triplet state. So it is called intersystem crossing. That is S1 to T1, the liberation of heat, that is intersystem crossing. That is another pathway. And another pathway, fourth pathway, after ISC, the molecule in the T1 state liberates its excess energy in the form of radiation, and it becomes in the ground state. This is called phosphorescence. This path is radiative. That is the radiative transition from T1 to S0 with the liberation of excess energy in the form of radiation. Now this process is called as phosphorescence. Phosphorescence means that is the radiative transition from excited triplet state T1 to ground state with the liberation of excess energy in the form of radiation. Now these are the various photophysical processes, that is IC, ISC, fluorescence and phosphorescence. This slide shows various pathways of deactivation of excited state molecules. Excited state molecule, that is non-radiative transition IC, ISC. These are shown in the slide. Similarly, radiative transition, fluorescence and phosphorescence also shown in the slide. So non-radiative means liberation of excess energy in the form of heat. Radiative transition means liberation of excess energy in the form of radiation. Once again, this slide shows explanation about non-radiative transition and radiationless transition. So non-radiative, radiationless, both are same. So in this topic, uh, what are the transitions? One is IC, another one is ISC. IC and ISC are non-radiative transition or radiationless transition. Now IC means internal conversion. IC means non-radiative transition from higher excited single state SN to the lower excited single state S1 or ground state S0. That is IC. Another one is non-radiative transition from higher excited triplet state Tn to lower excited triplet state T1. That is also IC. Now simply non-radiative transition from higher excited state to the lower energy state with the same spin multiplicity, that is called IC. That is Sn to S1 with the liberation of heat, that is IC. S1 to S0 with the liberation of heat, that is also IC. And T1 to T1 with the liberation of excess energy in the form of heat, that is also IC. So all these are internal conversion processes. Next one is intersystem crossing. Intersystem crossing, that is simply ISC. Now non-radiative transit from higher excited singlet state to the lower excited triplet state T1, that is ISC. Or non-radiative transition from higher excited triplet state Tn to the lower excited state S1 or S0, that is also non-radiative, that is also ISC, intersystem crossing. So simply it is non-radiative transition from higher excited state to the lower state with the different spin multiplicity, that is intersystem crossing. That is Sn to T1 the liberation of heat, that is ISC, or T1 to S0 with the liberation of heat, that is also ISC, or Tn to S1 state with the liberation of heat, that is also ISC. Here Tn where n is greater than 1, that is T2 to S1 or T3 to S2, etc. So these are the intersystem crossing processes. So that is, these are the photophysical processes. One is IC, another one is ISC. Both are non-radiative transitions. This slide shows explanation about radiative transition. So radiative transition, there are two types. One is fluorescence and another one is phosphorescence. Now fluorescence means radiative transition from first excited singlet state S1 to the ground state, that is fluorescence. But in the case of phosphorescence, that is radiative transition from first excited triplet state to the ground state, that is called phosphorescence. So excited singlet state to ground state, radiative transition, that is fluorescence, and radiative transition from excited triplet state to ground state, that is phosphorescence. Yeah, ground state is always singlet state. So this slide shows various radiative transitions. Explanation about radiation transition. Now next topic is quantum yield or quantum efficiency, and the symbol is pi. It is the term used to express the yield of photochemical reaction. That is the quantum yield is the term used to express the yield of photochemical reaction. That is number of molecules reacted by the absorption of one quantum of radiation. In other words, that is number of moles reacted by the absorption of one Einstein of radiation. Now what is the difference between quantum and Einstein? One Einstein. One quantum which has energy epsilon is equal to h nu. But in the case of energy of one Einstein, that is E is equal to n h nu, where n is the Avogadro number. Einstein is nothing but Avogadro number of quanta. So one Einstein, that is the energy of Avogadro number of quantum of radiation. That is called Einstein. So it is number of molecules reacted by the absorption of one quantum of radiation. In other words, number of moles reacted by the absorption of one Einstein of radiation. So these are given in the formula. One more formula, pi is equal to rate divided by intensity of light absorbed. That is also formula to determine the value of quantum yield pi. So far we have discussed 1.1 portion of physical chemistry 2 syllabus in photochemistry. So in photochemistry there are two titles. One is 1.1 another 1.2. We have covered 1.1 portion. We can see the 1.2 portion in the next presentation. Now this slide shows 4 steps to be followed in the critical situation of COVID-19 pandemic. What are the 4 steps? Be safe. Be a responsible citizen. Maintain social distancing. Wear face mask while going out of home. Thank you.